better.
Okay, good. Sorry about the technical difficulties. Okay, so yeah, I'm Xiangming Jiao from Stony Brook University, and I will talk about weighted squares remap for super convergent and non-oscillatory data transfer between non-matching meshes on surfaces. And this is joint work with my students Yipeng Li, Tiao Chen, and Xubin Wang. And this work is supported by the Kanga project of DOE, which is part of the SciDec. Okay, so this is the outline. We'll first briefly introduce the method and its challenges, and then some brief background. And then the core of the technique of our method is basically achieving superconvergence, detect discontinuities, and to overcome discontinuities. And then we'll show some numerical results. Okay, so introduction. So data transfer or remap is an important part in the partitioned approach for multiphysics coupling. And as physics models are getting more using high order methods, then data transfer also need to be high order. However, high order methods like interpolation and even some low order methods can cause spurious oscillations near discontinuities. So this is one example for L2 projection, common refinement-based approach where there are oscillations near the discontinuities, and this is another radial basis function-based approach, which is highly oscillatory near discontinuities. So these are similar to the Gibbs phenomena in Fourier transformation. So the goal of this work is basically to resolve Gibbs phenomena in solution transfer, data transfer. And there are various methods developed, especially in the context of solving hyperbolic partial differential equations, such as Wino schemes for finite volume methods. Wino stands for weighted eccentric non-oscillatory schemes. And in the context of hyperbolic PDEs, typically you only need to resolve C0 discontinuities or simple jumps, because the numerical diffusion in the numerical schemes will be able to handle C1 discontinuities easily. However, in the context of remap, we don't make assumptions about numerical diffusions in the physics models, and hence we need to resolve both C0 discontinuities and C1 discontinuities, or simple and derivative jumps. So in that sense, actually it's harder to achieve non-oscillatory behavior in remap than in PDEs. So here, basically, we will solve the problem given a source mesh and target mesh, and the function values on the source mesh at the nodes. How do we compute the nodes at the values at target nodes to high order accuracy? And besides achieving high order accuracy, we don't want to have oscillations near discontinuities. And the background. So our approach is based on weighted least squares. So the keyword is weight. And weighted squares is derived based on Taylor series. It's similar to interpolation. You have suppose you have a smooth function f, and you have a point u naught in Euclidean space, and you have a collection of points in its neighborhood or the stencils, right? So you can build if you have m points, you can build a system of m equations. And this is what we call a generalized van der Waals system on the left-hand side, A, which is a generalization of interpolation, which uses a square van der Waals system. So basically, to solve this system, we formulate it as a minimization of a weighted norm instead of just a two norm. And the weight is an important part of the model, and that's what we are going to focus on later. Okay, so given the weights, and we have the W times A, this matrix, okay? And this system in general can be U-conditioned, and to resolve that, we first apply equilibration on the right-hand side, on the right of A, by doing column scaling, and then solve it. Even with this scaling, it can still be U-conditioned, and we use truncated QR with column pivoting to solve it basically you truncate higher order terms automatically if the system is unstable. And it monitors the condition number of this matrix A tilde. And it will remove rows by doing truncation, or if necessary, add more points to the matrix so that it's stable. And so we use WLS in two methods. One is what we call continuous moving frames, which is similar to what is known as moving least squares. So this is for surfaces. Right? On the surface, basically, we don't have a global coordinate system. Well, we have a global coordinate system, but we don't want to use it. Instead, we build local coordinate systems. So at each point, you have a normal direction. Each node, you have a normal direction. And then you are basically from that, you have a tangent plane. And so the question is that away from the nodes, what do you do? So basically, in continuous moving frame, we linearly interpolate the normals of the nodes to build the C0 continuous normal direction, and from the normal, and then we build tangent plane, and then build the local coordinate system. So the local coordinate system is what is the moving frame referring to, and it's C0 continuous. And so this is similar to moving least squares, except that we only enforce C0 continuity instead of C infinity continuity for the coordinate system. And then moving weighted averaging of local fitting, or WALF, is a different approach. So basically, for every point that we want to interpolate, we only build polynomial fittings at the nodes of the mesh. And then for the points inside the elements, then we basically will interpolate by taking a weighted average of the polynomial fittings from the nodes. So basically, for example, x1, we get a polynomial fitting, a dotted curve, and for x2, we have a dashed curve. And then for any point in the middle, we have one interpolated value from x1 and one from x2, and then we take the weighted average in between them. The weights is basically the finite basis function, or the barycentric coordinate for simplicial elements, CMF and WALF. So that's why we this case of.
Jim, we lost your audio.
Oh, really? Sorry.
Just briefly.
Okay. Is it working now?
Yes.
Hey. Okay. I don't know what happened. So for WALF, the major thing, well, WALF is more efficient, but the most important feature for this talk is that WALF is quite unstable near discontinuities. So actually, we are going to take advantage of the instability to detect these discontinuities. So we'll come to that later. Okay, so now we'll focus on the main methodology of WSENO. So here is the flowchart of overall algorithm. It takes input meshes and field variables. And well, there's a pre-processing step to find the association of the nodes between the source and target meshes. Basically, for the target node, to find the neighborhood for on the source mesh. And then the core are basically these three parts. This box here, we will basically transfer smooth functions. And then this diamond has to detect discontinuities. And after we detect discontinuities, we are going to change the weights to achieve eccentric non-oscillatory transfer near discontinuities. So these are the three key components. And finally, it's going to get the solution values on target mesh. So as I said earlier, the key component in WLS is the weights. How do we use weights? Now, for many methods, like for solving partial differential equations or high-order surface reconstruction on meshes and so on, the inverse distance-based weights work very well for different degree polynomials. So they have different asymptotes. And essentially, by using different asymptotes, they encourage error cancellation. and you basically get similar to high order convergence, like super convergence in center difference schemes, where you get second order accuracy instead of first order accuracy on non-uniform meshes. So basically, the weights can achieve similar things on unstructured meshes. Now, in the context of remap, what we found is that so the inverse distance weights have this disadvantage that it's have a very steep slope near the center, and if you happen to have like a target node, and and on the source mesh you have the nodes that are pretty biased on the source mesh. So this you have some points that are very close to this node, and then what happens is that the node that's closest to it is going to have a very high weight, and it basically destroys error cancellation, and there is no more super convergence. So to overcome this, we looked at some radial basis function. They developed some C3, C4 continuous weights. So for example, here it's very flat because it's C3 continuous, and then there are some parameters, and we adjust the parameters so that they basically have the same asymptotes as the inverse distance based weights. So there will also be good error cancellation far from the center point, and near the center point, because it's flatter, it's like unit weights, similar to unit weights, and it has better error cancellation also. So this was developed specifically for remap. And so in the Bowman's weights, it's locally compacted. It means that the weights comes to zero at some cutoff radius. And that can be problematic if you cut off too early, then you basically have a degenerate system. So basically, to choose the cutoff radius, we have two criteria. One is that we make sure that there will be at least 1.5 times the number of coefficients, of the coefficients in terms of the number of points. So, for example, if you have 10 coefficients, we want to have at least 15 points in the neighborhood. So from that, we choose this R. And then the cutoff radius is sigma times R, and this sigma is required to be greater than 1. Okay. And now, how do we choose this sigma? That's another important question. So it turns out that if the weights are smooth enough, like C3, C4 continuous, then the error actually have this V shape when you increase sigma. So there is a optimal point, optimal choice of sigma where the error is minimized. Now, we compared 3 different radial basis functions. Bowman's weights is a non-polynomial. Wu and Vanderland, those are optimal polynomial basis functions we see for discontinuity in the sense that they are the lowest degree. But Bowman's weights, it's even lower degree, it's a C3. And Bowman's weights, they tend to be actually have the smaller neighborhood and smaller errors. So we use these Bowman's weights. Now, Wu's weights and Vanderland weights, they are used in literature, such as in DDK. But we are the first ones we use to find that Bowman's weights actually perform the best. So this gives us optimal accuracy among these choices for smooth functions. Now, what about discontinuities? That's the key question. So for discontinuities, we need to first detect discontinuities. And to do that, the bottom line is that we use WALF. So as I said, WALF is quite oscillatory near discontinuities. So it's far more oscillatory than CMF. So it gives you overshoot. And at the same time, if you use linear interpolation, it's going to be very flat, very smooth, no more oscillation. So what we do is that we compare WALF against linear interpolation. We use that to compute an indicator alpha value. And so we can actually do Taylor series expansion to analyze this asymptotic behavior of alpha. So in smooth regions, alpha is going to be second order. And if it's C0 discontinuous, then you can use the limit to see that it's unbounded, it's order 1. Well, not unbounded, sorry, it's order 1. It does not diminish as the mesh refines. And if C1 discontinuity, then it's order H. So there is this clear gap. And then how do we choose the threshold for alpha? Now, we want to choose the threshold such that the threshold is going to have at least a square root of h gap with the true values. So this leads to this threshold based on local variation of the function value and global variation of function value. And we ensure that there is at least an order of h, square root of h gap. So the detection will be very accurate in terms of alpha. This is for element. Now we are doing node-based transfer. So we need to transfer the element-based indicator to nodes. And for that, we basically take the neighborhood of the node and then evaluate its variations against the total sum of the absolute values. So basically using this as the main criteria and then a couple of safeguards against division with small values or division by 0. And from this formula, we can actually derive a theoretical value for beta for smooth functions. And then we can choose a value so that it is large. I mean, it's a clear gap between smooth and discontinuous regions. So here is an example where you have discontinuous functions with C0 and C1 discontinuities, and you can see that beta blows up at C0 discontinuities, and they are pretty large at the C1 discontinuities, and they're zeros, basically zeros in smooth regions. So it has a very, very clear cut. And that's what we want because it's this is guaranteed based on the Taylor 6 expansion analysis. And so this gives us the values on the source mesh and on target mesh. Now, if a source node in the stance of target node is marked as discontinuity, then we consider that node as discontinuity. Okay, so this allows us to detect discontinuities very robustly. So in ReNo, ENO schemes, there are also indicators, but they are not very robust. They only detect CZ discontinuities and so on. Now, with that, we need to introduce a weighting scheme near discontinuities. Basically, the idea for the weighting scheme is to make it essentially one-sided. So, two-sided center difference is unstable. We have discontinuities. Over there, you want to switch to one-side differentiation, right? So the weighting scheme essentially makes the differentiation one-sided. So you make the weights on the other side to be close to 0. The other side of discontinuity to be 0 or close to 0. So basically, this is the idea. And the major part is this f minus g0 squared, and g is linear interpolated value. And this gamma is a safeguard against the geometric discontinuities. So it takes the normal directions, the angle between the normals. And here, this is a safeguard against the C1 discontinuity. So if we omit this term and set gamma to be 1, then essentially it's the same scheme as in the original weak squares ENO scheme for hyperbolic conservation law. And for Remap, we have to introduce this new safeguard for C1 discontinuity. So that's the key idea. Now I'm going to show some numerical results. Because this is developed for Kanga for the climate modeling, and we test them on spheres instead of general surfaces. And so these are a couple of smooth functions. And this slide shows the convergence after one step of solution transfer using different degrees of 2, 3, 4, 5. And so basically for even degree, there is a super convergence. For degree P polynomials, it gets slightly higher than P plus 1 convergence rate up to P plus 2. And that's what we want for using those weights to encourage error cancellation. And so this is for repeated transfer after 1,000 steps, and the accuracy are also very good. Also have super convergence. For example, degree 4, it almost have a 6th order convergence. So this compares the conservation error as well as dissipation. So here, we can look at L2 projection, which is conservative in 2D, except on surfaces there are some geometric errors. And when we use weighted squares 3 or 4, it beats the conservation of L2 projection. So basically, to have good conservation property, you either need to enforce conservation strictly for low order methods, or you switch to a high order method. Then you have a similar or even better results than low order conservative methods. That's for smooth functions, this. And now for discontinuous functions, there are a couple examples for function f3, f4, and on the surfaces. And these are the detected discontinuities. And you can see all the discontinuities are detected correctly. There are no false positive or false negative, but except that there is a finite width, like 2 or 3 cells wide. And after we detect discontinuity, now here this shows why it's important to resolve C1 discontinuities. Now, if we in that WS-ENO scheme, if we set C1 to be 0, then it only considers C0 discontinuity. And you can see that after 500 steps, there are some obvious artifacts with C1 equals 0. And after 1,000 steps, it becomes worse. And if we resolve C1 discontinuities using this coefficient C sub 1, and then we don't have those artifacts, so the solution looks very uniform. And now, compared to other methods for Gibbs phenomena, now this is for linear interpolation, right? With one step, nothing will go wrong in one step. And moving these squares in DTK, it has a slight oscillation, and L2 projection is similar. And real basis function interpolation, it's very, very bad in terms of oscillations. Now, in repeat transfer, we only compare the good ones, and linear interpolation is highly diffusive. DTK is always oscillatory, it preserves the oscillations. And WS-ENO, yeah, it's as you expect, it's very good. And when we use different degrees, then we say that for degree 2, 4, and 5 degree, for finer meshes, they are all comparable. For coarser meshes, degree 4 is actually the best, because degree 2 is not accurate enough. Degree 6 requires too large neighborhood. It becomes more diffusive. So our recommendation is to use degree 4. So in conclusion, we developed a new method called WS-ENO remap for transferring data between non-matching meshes. We developed new weighting schemes for smooth functions to achieve superconvergence, and new techniques to develop to detect discontinuities and to overcome oscillations near discontinuities. So our conclusion in terms of numerical experimentation is that it's optimal to use degree 4 polynomials in smooth regions and reduce to degree 2 polynomials in discontinuous regions using the ENO weights or ENO weights. And it achieves higher order accuracy and low dissipation in smooth regions, and non-oscillatory and minimally diffusive near discontinuities. And this talk only covered node transfer, and we have recently extended to cell average values, and VJ is going to give some preliminary results we had, and we have further improved those results recently, but they will be published later. And this talk is based on a recent paper published in JCP, and here is the link for it. Okay, thank you.
Thank you, John.
Yeah, okay.
Any questions?
All right, sorry about the technical difficulties at the beginning.
That's quite all right.
Okay, any questions?
Jim, I have a question. Did you compare the WS-ENO method with the L2 projection with monotone limiters, let's say? Because you showed the Gibbs phenomena.
Right. Yeah, monotone limiters, I mean, they basically reduce to first order if you are not careful. That's not good enough.
Sure.
Yeah.
Okay.
So for example, if we reduce WSE0 to linear in discontinuous regions, it's going to be very bad. It has to be at least quadratic near discontinuities. Right. So if you have used limiters, ppm and so on, it's at least quadratic. You want to have quadratic polynomials near discontinuities.
Mm-hmm.
Right.
And can you also make a statement about maybe the computational complexity? Is it more expensive, less expensive, relative?
Yeah, that's a good question. So I did not mention in the algorithm. Okay, so basically this step and this step, they are computed using matrix vector multiplication. So even the indicator, that's a matrix vector multiplication. We pre-build the operators and then detect it, and then locally we near discontinuities we are going to do a local transfer. So the efficiency depends on how many discontinuities you have. So you have localized discontinuities, then it's going to be very efficient. So that's our assumption. The solution should be smooth almost everywhere, and near discontinuous, it's going to have more cost. However, it's still linear time complexity. There is no global solver for linear systems and so on. So it's still highly parallelizable. Linear time complexity overall.
Thanks.
Okay, thank you. I'm going to stop sharing.
Okay, Vijay, you're up next.
Yeah. Are there any other questions for Jim before we move on?
I think we're good.
Okay. You see that okay?
Yeah.
All right, so we'll get started. Hi, I'm Vijay Mahadevan from Argonne National Lab. I'm presenting joint work, ongoing work with a couple of people, Jorge from NCAR, Paul Yolik from UC Davis, and several other people from National Labs. So the topic that I'm going to be presenting today is about a comparison that we are currently doing about different higher order remapping schemes for climate models, and more specifically looking at accuracy and stability of these remapping schemes. First, I want to acknowledge some of our funding sources. This is funded mostly by Kanga, and bulk of this work also had some funding from P3SM. So this is a brief overview of my talk. I'm going to give you some background and motivation for why we are doing this intercomparison work, some challenges in remapping, how we want to address that, and how the intercomparison implementation looks like currently, and some highlights at the end. The coupled climate models are complex beasts, right? So this is a sample hub and spoke model, and they are typically they sit at a 1 degree separation from every other component, and so any inaccuracies that you make in the coupler tend to propagate pretty quickly to the other components. I'm sorry?
The third one. The one on the no, the second one, sorry.
I didn't quite hear what you were saying.
Does somebody have a question, or was someone's mic on? Just go ahead, Vijay.
Okay. So it is important to actually maintain temporal stability and accuracy. That is, how do you treat a couple nonlinear terms between the components so that you don't introduce new inaccuracy. The next is the spatial component of the coupling, which is you transfer. There are nonlinearly coupled fields between the components that need to be transferred, and each of these fields are represented in unstructured grids that are specific and scale resolving for that particular component. So how do we make sure that these field transfers are conservative and that we don't introduce any new instabilities or inaccuracies? So that's a fundamental challenge. We're going to be focusing in this talk specifically about the spatial remapping schemes. So what is Remap? Remap is basically the process of transforming and migrating the field information between component grids. And remember, these are very different resolution grids, and they could have very different topology as well. So there are many schemes. There's been a lot of previous work. This is specifically for climate models that are listed here. And some of these variants are based on L2 projection. And there are also other schemes that are globally conservative, but not necessarily higher order, at least not more than second order. And there are also many interpolatory schemes and some that's based on mesh-free methods. And one example is what Jim just talked about today with the weighted Reno schemes. And so what we did was we took 4 specific schemes to compare their performance and the numerics for some sample synthetic and real climate field data. So here there are 2 mesh-based remappers, and both of these use some variation of L2 projection to get higher order conservative maps. One is from the Earth System Modeling Framework, another is the Tempest Remap, provides conservative and consistent remappers with higher order projection. And the next 2 methods are based on meshless, and one is the generalized moving least squares method with a variation to also include a normalization for global scaling and also in addition for local bounds preservation. I'll just briefly touch upon that later on. And the next one is the weighted least squares, essentially non-oscillatory remap, which Jim just talked about earlier today, but this is specifically for cell-to-cell transfer. So what are the main challenges in remapping? What we want is certain properties to be met, and given that this is a really complex process of transferring data between unstructured meshes, we want to make sure that the underlying algorithm is insensitive or algorithmically invariant to the mesh topology. So this is the cube sphere grid, this is a lat long, and this is a MPAS polygonal mesh. This is a regionally refined grid. So immaterial of which grid we use, we want to make sure that other properties do not suffer. And what are these other properties, right? So we want to ensure both global conservation. So this is a really smooth solution with an L2 projection and a minimization that I show here. And this is a really simple problem. So we are essentially doing a remap, so it's globally conservative. But when we have sharp gradients, the L2 projection could introduce oscillations. And this is the Gibbs phenomenon that Jim talked about. So even though the area is accurate, you could actually introduce spurious oscillations. While with interpolation, you're not globally conservative or locally conservative and completely inconsistent as well. So these are important things to watch out. The next is consistency. So when we transfer solution from a source grid to a target grid, can we retain the discretization order on the original source grid and the accuracy in the given norm? So here I show the L2 norm errors and the H1 norm errors, and this is for a generalized moving least squares problem. Just to give you a demonstration, for different degrees, the order of accuracies are what we would expect. In fact, here for the 4th degree, I have super convergence, but that's great. The idea is we do not lose any accuracies. Next is monotonicity. So if my solution on the source grid has a certain global bound, can I preserve that global bound after transferring the solution? And so you could apply monotone filters to achieve that. But in terms of a metric, we measure that by looking at the solution before and after the projection and the departure away from these global bounds. And in the same flavor, we also look at it in a local bound as well. So this gives us a measure of dissipation in the solution So if you have local variation in the solution, after remapping, what happens to those local bounds? Do they move away from those local bounds, or do they get dissipated? Do they get flattened out? So that's the measure that we want to see here. And all of these are very important properties, but not all of them can be met simultaneously. It's a complex problem, right? So coming back to our schemes that I introduced before, the L2 minimization, which is mesh-based, it's implemented in ESMF and Tempest Remap, different flavors of it. But essentially what they're trying to solve is this minimization problem, where G is the functional on the source grid, and F is the functional on the target grid. And so what we want to minimize here is the global integral. And you can expand this out essentially as the weight matrix here is essentially a mass matrix that depends on the basis functions defined on the source and target grid. And so that's important to get this weight matrix correctly. We need to make sure that there is an accurate intersection between the source and target grid. So what we call super mesh, that needs to be computed. Let me see if I can. Okay, let me skip the video for now. We can come back to it later if needed. But essentially, there is an algorithm that computes the intersection between two grids, and we use that to compute this global integral. And the accuracy of the scheme depends on the reconstruction, especially with finite volume to finite volume transfers. It depends on the patch that you use to reconstruct your basis. And you can achieve higher order accuracy by expanding that patch. We also need to impose conservation and monotonicity constraints if you want to eliminate those spurious oscillations that I showed before through Gibbs phenomena, right? On the other end of the spectrum, we have the meshless remappers. First, I'm going to touch on the generalized moving least squares. The generalized moving least squares can actually take more than just the point data. And so these are meshless, so they just look at the vertex data. But you can include the normal data and the tangent derivative data, and also cell averages or anything more as inputs for the generalized moving least squares. Your objective function can also be a lot of different things, and so it gives you a lot of flexibility in how you want to impose this remapping scheme with generalized moving least squares. This is harder to do with just moving least squares. That is, for example, implemented in DTK. But we're going to be specifically looking at one implementation that uses a composite toolkit from San Diego National Lab. It's exposed through a Python interface, and most of the results that I'm presenting today with GMLS uses this particular implementation. There is also a variation that was implemented using the clip and assured sum CAS method by Andrew Baddeley. It uses this monotone filter called QLT that is computationally extremely efficient and preserves local bounds, and it's important for property preservation. We can apply this as a post-processing step. The next series is the WSENO scheme. I won't go into too much detail here since Jim just gave a talk, but what I want to mention here is that it uses C3 radial functions, and there is feature detection for C0 and C1 discontinuities. And Jim also extended this recently for cell average data, which is not published yet, but we are using that in this intercomparison study as well. Now, what does this implementation look like for this intercomparison between different remapping algorithms? So first, we pick different grid types. So one is a cube sphere, another is a lat long grid. The next is a MPAS type polygonal mesh. And we also picked 5 different fields that were sampled on each of these grid types of different resolutions. So each grid was also uniformly refined 5 times. So you have 5 resolutions and 5 fields that were sampled on each of them. And we take these different remapping algorithms as black box operators, and we apply it multiple times in terms of remap iteration. So that is what I mean by remap iteration is I have a sample solution on the source grid, I transfer the data to the target grid, and then I bring it back to the source grid. That's one remap iteration. And we did thousands of remap iterations, and then we passed it to the metric computation, which is based on a Python implementation that is open source, available here. And we implemented several metrics for in this particular implementation, which looks at conservation, different accuracies, the locality metrics, and the global and local bounds as well. I'll just briefly touch upon what these look like. So this is the synthetic fields that we use to measure especially convergence and order of accuracy. So this is a combination of two spherical harmonic functions. The next is a slightly smoother spherical harmonic function. And these are the synthetic data sets that we use. We could actually sample anything else if needed. And we also chose 3 specific real field data, which are obtained from composite satellite observations. So one is the total precipitable water. This is a contour plot of how that looks. The next is a cloud fraction. And what I also want to point out here is that some of these fields have strict bounds. So the cloud fraction here is between 0 and 1. And the global topography is pretty widely varying, in the sense it's about minus 11K here to about 9K at the upper end of the spectrum. And so during these remapping studies, we want to make sure that those bounds are also met, right? And just a summary of what the metrics driver does, essentially, it computes different error norms, global conservation, monotonicity, like I said, the global maxima and minima, and a locality as well, norms in the local min-max bounds. Now, give you some highlights. These are not all the results. These are just a brief subset of what we have. But first, let's look at the error convergence from different remapping schemes with different degrees of reconstruction. And all of this is with the finite volume to finite volume projection. So this is with Tempest Remap, conservative Tempest Remap application. And so with degree 1, we are seeing order 2, degree 2, we are seeing order 3. Degree 3 is not quite order 4 as we would have expected. And the H norms are also matching what we expect from a theoretical standpoint on these reconstructions. But this sort of a metric study also helps us to go back and improve these remapping algorithms. And similarly with the ESMF, with degree 0, we're getting first order. With degree 1, we expect a second order, and we are not. So this is something to look at. How do we obtain higher order accuracy with these L2 projections? So perhaps there is some parameters that are missing, so we need to go back and refine those. But with these meshless schemes, with degree 2, we're getting order 3, and the gradient norms are order 2. And similarly for degree 3, we're getting order 4, and the H norms are showing some superconvergence here. And for degree 4, we have really high superconvergence, so those are order 6. And so that's good. And this is for a really smooth analytical field, the analytical function 1 that I showed before. And the WSE-NOR has a very similar behavior as well. And as Jim mentioned, there are very similar flavors in this WSE-NOR scheme to the moving least squares. And so this is not really surprising, but we are able to achieve higher order accuracy with these meshless schemes. In terms of global conservation, when we apply this scheme and we perform 1,000 remap iterations, so what happens? So we chose specific degrees on each of these methods, and the top plot shows the cube sphere to M-pass projection, and the bottom shows the M-pass to a lat long grid. So we see specifically here that the moving least squares perform pretty badly in terms of conserving the global integral in the data. While if you actually apply scaling to it, which is essentially just a normalization, you can achieve the global integral, which is not surprising. But the ESMF first order and second order conservative scheme performs the best here in terms of the L2 projection. And the WS-ENOR scheme actually does not conserve globally. But perhaps there's a lesson to be learned here that if we use some variation of a scaling, maybe we could achieve better global conservation. So that's something that needs to be explored. The next is, this is for a total precipitation water. We have a similar behavior as well, just like the crowd fraction field that I showed before. For monotonicity, this is the global max, global maxima. Similarly, we also have a global minima that I'm not showing here. And just like the previous result, the top one is the cube sphere to impasse, and bottom is the impasse to lat long grid. It is surprising that the ESMF remapper actually becomes more accurate in terms of preserving, in terms of converging towards the global maxima. What I also want to point out here is that the WS-ENOR scheme is not shown here, mostly because the monotone, or it's not monotone, the limiters that Jim uses in his cell-to-cell transfers actually accurately achieve the global maxima, and it pins it there. And so the error difference between the maxima on the exact solution and the maxima on the numerical solution is 0. And so the WS-ENOR scheme does not show a plot here, but that just means the WS-ENOR is actually more accurate, and the Tempest remap performs well in terms of keeping it bounded. None of these remappers actually blow up, and those are good things. And the total precipitation has a very similar trend as well. Here, the WS-ENOR stays flat, and so definitely that beats most of these other methods, and that's overlaid on top of the Tempest remap solution here. And the GMLS and the ESMF actually performs the worst in this particular case. So what I want to stress here is that the performance of these different remapping schemes also depend on the solution profile. It could be really property preserving for one field, but not necessarily for the other field. That's something to take into account. The next is local dissipation. So here I'm plotting the local L2 norm of the local field maxima. And similarly for this is cube sphere to impasse and impasse to RLL. And Tempest remap performs really well in terms of preserving that local structures, local features in the solution, and it keeps it bounded with very less dissipation here. And this is with the higher order conservative map. And the meshless WS-ENOR scheme also performs just as well in terms of preserving those local features for the cloud fraction. And with total precipitation, again, the WS-ENOR and Tempest remap are right on top of each other in this particular case. And the ESMF is extremely dissipative, as we can see in both this slide and the past couple of slides. And so in summary, what this particular talk is about is we compare different remapping schemes. Traditionally, we have always used first order remapping schemes, but with E3SM and as a broader community, we want to explore these different remapping schemes and look at the properties given different constraints, given different fields, given different mesh topologies, what happens to these remapping schemes and the numerics of it. And so we see that global conservation is generally achieved with L2 projection and obviously with normalization, but you lose in terms of also achieving low dissipation if you do normalization. But schemes like WS-ENOR for cell-to-cell transfer can still provide very low dissipation while achieving higher order accuracy. So we are detailing all of this results in a manuscript that's being written right now. And this is just a start of a study. It can be extended, certainly, for many other cases. So one is for us to look at grid-to-grid transfers with topological holes in the target grid. For example, the ocean grid always has holes where there are land regions. So how do you make that transfer, and how do you achieve conservation and consistency for such a case? And if we have a higher order source solution, which is a spectral element solution on the source grid, then can we also achieve higher order projection using these different remapping schemes? And if there are other remapping schemes that are being used in production cases or that are still being researched, perhaps we can also include those in our. So that's where we are right now. Thank you.
Thanks, Vijay. Are there any questions?
Vijay, I just want to make a comment about WS-ENO for the global conservation. So the implementation we used for this comparison was basically a quick implementation using node-based transfer near discontinuity. So it was treating cell average value as cell centered values near discontinuities. So that's why it lost the conservation a lot. And
Okay.
we have, we implement the correct treatment, but haven't got results yet. So we will see how will that perform. But I think it will improve significantly.
Sure. This is so that was specifically for the cloud fraction.
Yeah, for all the discontinuous functions.
Sure.
I don't know whether you have a slide for smooth functions. For smooth conservation of smooth.
I did not include the smooth functions here, Jim.
Okay.
There's just a lot of data that needs to be consolidated.
I know. Yeah, for smooth functions, it performs very well. For discontinuous functions, because of that second order limitation near discontinuities, so it was not conservative.
Okay. Thanks for the update.
Hello, I have a question about the order of convergence. This is Julian.
Yes.
So when you determine computed this order of convergences, how do you compute it? You increase the resolution and you compare like theoretical limit with this, or
right.
And what was the resolution for these computations? I mean, do you start with any 100 or any?
So we started with coarse grids. So this was any 30.
And then you double, or how do you determine the order of content?
And then we just continuously refine uniformly. And similarly for the MPAS grid, there was a coarse grid, and then we continuously refine that uniformly. And so
so the question is, from what resolution to what resolution did you determine this number?
So the maximum resolution here was NE256 for a cube sphere. Okay. And something equivalent in MPAS, about 2 million elements on MPAS grid, the finest one.
Okay.
And so we sample the fields exactly on each of these grids, and the error is computed after one remap iteration. Oh, sorry. So the error was computed after one remap iteration. So this is the convergence based on one transfer to the target and back to the source.
Okay. And do you think how do you think you can do this when MPAS will have holes?
That it will be harder to make the convergence study there. because we'll have to think more about that, because it's harder to define an analytical field on a mesh with holes. So it's something that needs to be discussed. Yeah, it'll be in our next work, future work.
Okay, thanks.
Okay, we should probably move to the next talk.
Thanks.
Thanks, Vijay. So next up is Han Zhang.
Sorry, I muted myself.
It looks good.
Hi, everyone. I'll just start. Okay.
Yeah, go ahead.
So atmosphere and ocean affect each other through the exchange of heat, momentum, and water. And it's really difficult for a computational model to simulate all the physics. And also it's difficult to get the observations so that we can run a data-driven simulation. So I think that's one of the reasons why we need to couple the simulation. And coupled simulation becomes increasingly important for the accurate prediction of short-term weather and starting extreme events. However, there are two main challenges in the coupling models. The first challenge actually comes from the physical level. At the interface, we need interfacial flux parameterization, and another challenge comes from the numerical level, which involves the stability and mathematical consistency. So by stability, I mean what I mean by stability here is even if each component is stable by itself, the entire system is not necessarily stable when we couple all of them together. And if instability occurs in the system, it does not mean the solution may blow up, so it's not easily observable. But it may introduce spurious errors in the simulation, which is really hard to find. So to study the stability problem, well, first we abstract the problem into a simplified model. So this model is defined as two sets of PDEs on two domains, which are connected to each other at a common interface. In order to make this problem well posed mathematically, we usually need two additional conditions. One of the conditions, which is almost used everywhere, is the continuity of flux. The other condition could be the continuity of the state, or some more complicated interface condition like a bulk interface condition, which I will introduce later on. So these additional conditions are entailed by the algebraic equation 1c here. So in practice, instability usually occurs in the direction normal to the interface. When that happens, these equations will reduce to being one-dimensional. So that's why we want to restrict our attention to one-dimensional problem. In particular, we focus on one-dimensional diffusion equations, which governs the thermodynamics in ocean-atmosphere coupling. But note that the stability of one-dimensional problem is necessary for the stability of higher-dimensional problems. So if you care about the stability of 2D or 3D problems, you have to satisfy the stability of the 1D model first. Now the question is, how do we estimate the interfacial flux? So in climate modeling, there's a famous theory called Moline-Uphoff similarity theory, which parameterizes fluxes as a function of the dimensionless height parameter. Based on this theory, people developed the bulk formula, which is shown in the middle of this slide. And this formula is derived empirically from the observation. And it's valid only for hourly, roughly. And it has an accuracy of about 10 to 20%, which is not particularly high. So let's take the flux calculation for the sensible heat, for example. So this heat flux is approximately a linear function of the difference in air C temperature. It also depends on the wind speed difference between two locations. So one of the locations should be at the bottom of the atmosphere, which is 2 meters or 10 meters above the surface. The other location is about the top 1 millimeter of the sea surface. So we can see that the bulk interface condition is quite different from the interface conditions we normally see in other coupled systems. For example, coupled systems in fluid structure interaction problems, where the requirement being the states and fluxes should be continuous. So in our case, the bulk interface condition ensures flux consistency, but it allows jumps in states. So which means that the temperature at the bottom of the atmosphere can be different from the temperature at the sea surface. And the difference in temperature is taken into account to calculate the interfacial flux explicitly. So the reason this condition exists is, I think it's because of the limited resolution and excluded physics. So for example, if we have infinitely small grid size, we may see the temperature is continuous at the micro scale. And also there are missing dynamics in the governing equations. To capture the missing dynamics, we may need a molecular dynamic simulation. But anyway, this is the only practical way to compute the interfacial flux currently. And Farewell developed this famous algorithm called Corey in the 90s. And this algorithm has been continuously improved. It's currently being used by E3SM as well. Stability analysis for bulk interface condition, I would say there's not much work on this direction. But however, there are quite a few works on the stability analysis for another interface condition, which assumes that both state and flux are continuous. It's also usually called the Dirichlet-Neumann condition because of the way they are implemented. So for example, the first condition can be implemented as a Dirichlet condition, boundary condition for one model, and the second equation can be implemented as a Neumann boundary condition for the other model. The Gels in '97 had a very famous paper in the CFD community, and he used the normal mode stability analysis to study the stability for Dirichlet-Neumann condition, and he found that the coupling is stable if one imposes Dirichlet condition on fluid and Neumann condition on structure. And Lemary borrowed pretty much the same idea in 2015 and used the idea on the stability analysis of concurrent coupling algorithm for ocean-atmosphere coupling. And he points out that if we use Dirichlet condition on atmosphere and Neumann condition on ocean, the simulation can be unstable for certain parameter settings, but it can be stabilized by inverting the conditions. So the conclusions from these two papers are consistent with each other. So following the same idea, the first thing we did is to revisit the same stability analysis. So we also used the normal mode analysis to study the simple model I just showed in the beginning. And first we consider a normal mode solution. So the normal mode solution depends on a scalar A to the power n and times k to the power j. So n is the time step index, j is the grid index. So you can see that this solution depends on both on time and the space. And when we plug this solution into the discretized equations, we end up with a set of algebraic equations. And here we need to note that there are two important parameters. R here is a ratio between the density heat capacity times the grid size delta Z. And D is nothing but the current number for diffusion. Okay, so the stability criteria here is the discretization is unstable if these algebraic equations admit solutions that satisfy the far-field boundary condition, which means that k approaches to 0 when the index j goes to infinity, and when a, the absolute value of a, is larger than 1. There's a simple way to interpret this. So we can say that the model, the capital model, is stable only if a, the absolute value of a, is always smaller than 1, and the far-field boundary condition is also satisfied at the same time. We looked into two different cases. We consider both the explicit time stepping and implicit time stepping, and we end up with different simplified algebraic equations in the end. So see if, equation 4 and 5 respectively. So it's hard to establish a closed form relation between these parameters. But however, we can prove that when using explicit methods, the coupling is stable if the normal CFL condition is satisfied, which means that D is between 0 and ½ And for the implicit time stepping, we can prove that the coupling is not unconditionally stable. So this is kind of counterintuitive, because what it means here is even you use the implicit time stepping to solve the PDEs, you cannot achieve absolute stability because of the way the interfacial flux is calculated. So why our results are different from the previous results? So it actually comes down to the way we handle the interface node. So in our settings, we actually have a cell cross the interface, which is numbered 0. So the cell number 0, one of the bound is on the left side, and the right bound is actually belongs to the atmosphere. So the other bound belongs to the ocean. And if we derive the final volume formula for the interface node, let's say we integrate from the left bound to the right bound, we will end up with 2 terms on the left-hand side. But in Gauss' discretization scheme, they actually omitted one of the 2 terms on the left-hand side. So in the end, the stability depends on the ratio between the omitted term and the remaining term. If the ratio R is large, it will have relatively large impact to stability because this term is omitted. But if R is small, then it's okay. So that's the reason why they show if you do diffusion condition on one side and normal condition on the other side, it's okay for one case, but not okay for the other case. So I would not say their results are wrong. So it really comes down to how we treat the interface node. Also, our results suggest that this kind of loss of stability can be cured by modifying the discretization scheme. So now let's look at the more interesting problem, the stability analysis for bulk interface condition. Recall that the bulk formula defines the interfacial flux as a linear function of the difference in this LC temperature. And for simplicity, we define the coefficients before the difference, rho cc, capital CH, as a single new variable b. We call it this b. So note that this b is not a constant. This figure shows seasonal averaged values of this coefficient b for sensible heat flux. So thanks to my colleague He Wang for providing this figure. So from left to right, you can see the seasonal average average the values from spring, summer, fall, and winter. And this, you can see that this value x is relatively large in subtropical areas. So it's both time varying and spatially varying. So first of all, we start from a one-way coupled case. For example, if we consider the ocean alone model, we can assume that the temperature at the bottom of the atmosphere is a constant. It doesn't have to be zero, but for simplicity, we just assume it's a zero. Then the interfacial flux can be easily calculated. For bulk condition, again, we will consider an eigen solution, which depends on both time and space. And remember that the stability constraint will be the far-field boundary condition, which means that the kappa to the j term should goes to 0 when j approaches infinity. And at the same time, the absolute value of a should be smaller than 1. Okay, so now this time, our grid setting is slightly different because we don't have a cell that crosses the interface anymore. So now the interface between ocean and atmosphere is right at the intersection between these two computational domains. So first we consider an explicit flux coupling with implicit time-stepping method. So the reason we consider implicit time-stepping method here is we want to roll out the stability contributions from the inner domain. Let's say we already know that the component itself is absolutely stable. If there's instability, it only comes from the coupling at the interface. So for simplicity, we also define a new Coulomb-like number, which is beta. The beta depends on the bulk interface condition, the bulk coefficient B, and it looks very much like a Coulomb number for an advection term. And D is still the Coulomb number for the diffusion. And we insert the assumed normal mode solution back into the discretized algorithm and solve for A. We end up with the equation 7. And you can see that there are two different roots for A, but however, the positive sign is not possible. So we only need to consider the negative sign and consider two different cases, which is beta is smaller than 1 or beta is larger than or equal to 1. And finally, we can arrive at a very elegant theorem, which states that the stability condition should be beta should be less than or equal to 1 plus a square root of 1 plus 2d. So this theorem indicates that the coupling stability depends on both the Coulomb number for the diffusion and also the Coulomb-like number for the coupling for the bulk interface condition. There was a very interesting work from Belgium in 2017. They actually derived an empirical stability boundary for this coupling problem. And surprisingly, the empirical formula they derived in their paper is actually very close to the analytical condition we just developed. So a very important thing to note that is when D is 0, beta actually starts from 2. So it's not easy to see it from this plot, but recall that the intersection at the left bound should be 2. Okay, so what can we do if our simulation is in the unstable regime? By an unstable regime, what I mean is the residual for this constraint is larger than 0. To make it stable, we need to drive it from a positive value to 0. So naturally, people may think, oh, we can either reduce the step size or increase the grid size. But however, if you change the step size, both beta and d will be changed. So here we plot directly the relation of this residual and the step size delta t and grid size delta z. So you can see that this residual decreases rapidly as the time step decreases. It actually decreases more rapidly with delta t than the delta z. So this suggests that decreasing the step size delta t is actually a more effective way to push the coupling from an unstable regime to a stable regime. We also did some matrix stability analysis to validate our theoretical results. So by matrix stability analysis, we can rewrite the fully discretized equation in the general matrix form, which is A times Tn plus 1 is equal to B times Tn. The Tn plus 1, that's the solution of current time step, and Tn is the solution from previous time step. So for the matrix stability analysis, we need to calculate the eigenvalue of A inverse times B. So take backward order scheme, for example, the A and B are represented respectively as shown on the slide. So note that this analysis is really difficult to do in practice. That's also why we need a idealized model, hopefully simplified model to study the eigenvalues of this stability matrix. And here we show the results for the ocean. We can see that the stability region is actually smaller than we have seen for the one-way coupled model previously. We also considered implicit flux coupling. So here I would like to introduce the way we categorize the flux coupling. So we categorize all the existing coupling schemes into 3 categories based on the way interfacial flux is calculated. The first is the first scheme is called explicit flux coupling. This one is the most common strategy in practice. So what it means is people just calculate flux using the previous information, using the information either from the previous time step or previous time window, or it could be some average value in the previous time window. Another approach is the partial implicit flux coupling. This approach is not as popular as the first approach. So here we turn the index for t at half from n to n minus 1, which means that we add an additional unknown in the equations. So now that you see this t at half 1, this term becomes an unknown in the equation, and it has to be solved implicitly. And finally, the last category is implicit flux coupling. So in this case, we need to treat both t terms implicitly. So which means that we need the value of the other component for the future time. Because when we solve the current time step, we actually have no idea what the solution would be at time tn plus 1 for the other component. So this method is kind of difficult to implement in practice. So Belchers, etc., they came up with a very interesting method where they assume that tn plus 1 is just a linear function of tn, or essentially they're doing an extrapolation. They just estimated Tn plus 1 using the data collected from the previous time step. So essentially, they can achieve unconditionally stability. There are also some other approaches which is similar to the idea of implicit flux coupling. So for example, the iterative Shor's method, they do iterations. So essentially, you're like solving the fully complicit system. So okay, let's come to the results. We can see that both the partial implicit flux coupling and implicit flux coupling need to absolutely stable. So this is a very inspiring result because it actually suggests that to achieve unconditional stable, we don't have to do an implicit flux coupling. And actually, partially implicit flux coupling is sufficient to guarantee absolute stability. We also did this for both the ocean and atmosphere. So the top rows shows the results for the ocean, and the bottom rows shows the result for the atmosphere. They look similar to each other, except that the stability region for the explicit flux coupling is different. If you remember that the stability results we have shown for the one-way coupled model, you probably have already noticed that it's quite close to the stability results for two-way coupled model for the atmosphere. To further confirm this, we tried some different values of beta and d. So from left to right, we are increasing the values of beta plus and d plus. And you can see that the stability region for the ocean actually shrinks as beta plus and beta d increases. But if we look at the stability results for the atmosphere, the stability region stays almost unchanged when we vary the values of beta minus and d minus. So this actually tells us that the one-way coupled model gives a very accurate approximation to the stability results of the two-way coupled model, but for only the atmosphere. But it's not a good approximation to the ocean model. And the reason we actually have a theoretical proof in the paper. So I will limited by time because of the time limited. I will not go into the detail. To conclude my talk, we have performed normal mode analysis and matrix stability analysis. We investigated the stability as a function of coordinate numbers, and we established the stability condition for one-way coupled model. We also showed the coupled simulation tightens the stability constraint. And lastly, we showed that the implicitness of the interfacial flux is critical to stabilize the coupling. So in particular, our results favor the application of partially implicit flux coupling. For some ongoing work, we are extending this to two-dimensional models with advection. We are also using our theoretical results to identify regions vulnerable for instability using E3SM data. For more details, you can refer to our paper published on Journal of Scientific Computing. Thank you for your time. I'll take questions from here.
Thanks, Han. So in the time step that you may want to lower to increase stability for the 1D case is in a flow model would be like the coupling frequency, because there's no actual advection or anything vertically.
Right, that's correct.
Okay.
How I did not get it. So with the partially implicit fluxes, is the two-way coupling absolutely stable, or It's only the one-way coupling is astable.
Okay, good question. So as shown here, the partially implicit flux coupling is always stable, just like the implicit flux coupling.
So that's for two-way coupling. That can be proven.
Yeah. For one-way or two-way, it's always stable.
I see.
So
Very good.
basically, the instability can only occur when you do explicit flux coupling, which means that there's no implicitness in the flux calculation.
At Hong, that's contrary to the popular belief that you have to do fully implicit rather than just doing log Gauss-Seidel on the coupled system. Right. This depends on the coupling strength between the two models. Are you trying to generalize this, or is this specific to cases that you have looked at?
Can you repeat your last sentence?
I was asking if you are generalizing this result, or is this specific to cases that you're looking at?
A good question. So that's so currently this result applies to the one-dimensional diffusion equation, but we don't see any reason why it doesn't work for two-dimensional problems or problems that involve more complicated dynamics. Because for other models, I think we can do similar analysis as well. And actually, what we are working on is to consider the convection in the two-dimensional in the 2D problem.
Okay, that'll be interesting to look at for higher dimensional cases. If this result kind of extends.
Does this make any assumptions about which side is Dirichlet, which side is Neumann between the atmosphere and the ocean?
So the Dirichlet-Neumann condition is more of theoretical interest. It's, because of the bulk interface condition, we don't really do Dirichlet-Neumann condition in practical climate models. We always implement the bulk interface condition to that. So I think that analysis is probably more useful for problems outside of climate modeling. For example, the fluid structure interaction problems.
Right. Okay.
Okay, any last question for Han? All right, thanks. So our last speaker for the session is Chad Sockwell.
Can you guys see my slides?
Yes.
Okay, excellent. So I'm going to talk about a framework, the bulk method for coupling the atmosphere space. And the idea behind this framework is you can build splitting methods, ideally without splitting errors or by minimizing them. To really motivate the talk, I want to talk about the contention between ideal coupling scheme and the computational budget of a climate model. So I think Vijay already described the coupling scheme pretty well. It's kind of the glue that glues together components in a multi-physics simulation. And to me, some ideal properties of coupling scheme are the following. One, it should be partitioned. It lets you solve these components individually without being coupled. So it decouples them in some sense, so you don't have to solve some monolithic problem. Otherwise, I don't really think of it as a coupling scheme because you're just solving a big problem. Two, you want it to be stable, or you want it to have no time step restriction or a less restrictive condition than your model. So this goes kind of into Hong's talk and talking about the stability of these coupling methods. And then lastly, I also want it to be conservative. Namely, I want the flux that's passed between two components to be the same so that it sums to zero. That way I don't have like spurious mass or energy building up in my climate system, causing lots of issues over a long time horizon. Now, let's contrast this ideal coupler with the ideal of a climate model. In the context of this talk, you can think of a climate model as a highly specialized set of components, all requiring flux from each other, similar to the picture Vijay showed earlier in his talk, but with a very tight computational budget. And it's typically been the case that each component is vetted as much as possible, because there's no point in coupling unless you have components that work properly. Coupling is kind of seen as an afterthought. So all the computational budget is usually spent up perfecting these models. And then when it comes around to coupling, what's done in not necessarily all models, but in a lot of operational models, is effectively one iteration of Schwartz domain decomposition. And this is just an explicit data transfer where you take old data at the coupling step and pass it to the other model, and vice versa, the other models. And in the Lemery paper in 2015, they prove that this is unstable, completely unstable. But you have some saving grace, at least for some resolutions, where this error ability, which should blow up your climate model, can be mitigated by the artificial dissipation, smoothing, and mixing that exists in these models. And so the natural question to ask, especially for the E3SM model, which is meant to perform on exascale computers and have better resolution than ever, what happens to this process when the resolution? Well, your CFL condition becomes more restrictive associated with this coupling term, kind of like how Hong talked about. And your saving grace, this artificial viscosity or smoothing, the artificial viscosity on the smoothing gets smaller and smaller, of course, with resolution, because you don't want to smooth out all these nice conditions that you worked so hard to, all this resolution you got in your simulation. And so this really motivates the Kanga project and my project, and coming up with new, efficient, correct, non-iterative coupling methods that avoid this instability somehow. And so, succinctly, what you really want is a solution to the monolithic problem, potentially fully implicit, so you have no stability issues. So you just write down your problem monolithically with the coupling in there, one big matrix, and solve it. But you also want partitioning, meaning you don't want to have to solve this big matrix, but you want some way to break it down into smaller pieces that are decoupled. And so effectively, you want your cake, and you want to eat it too. And the question is, can you really do this? The answer is usually no, but maybe you can in this one special case. So let's think back about how this instability appeared in alternating Schwartz, at least my view of it. I think this problem kind of arises from this paradigm of partitioning these components to begin with and having specialists work on them, then coming back later and gluing these models back together. This is a super practical way to go about building a model. But I think once you have all these pieces built really well, you take a step back and say, we split up this model and we tried to glue it. Maybe it's not so obvious what to do when it's all broken up, little pieces, like putting a jigsaw puzzle back together. Maybe if we took a step back and looked at the big picture, if you could actually look at the cover of the jigsaw puzzle box and see how the big picture looks, it'd be a little more obvious what to do. So the idea is to derive this monolithic system and then see what kind of coupling schemes you can derive within it. And so a way to view this is a well-informed coupling scheme. You're utilizing some information of this monolithic system to come up with a better flux that has some desirable properties. And this is opposed to, let's say, a more agnostic coupling scheme, such as alternating Schwartz, where you just pass data. So the most straightforward way, and also the most expensive way to realize this well-informed coupling scheme, utilize the sheer complement of the monolithic system to produce these fluxes at the boundary, then producing boundary conditions for each individual component, and then you can solve them individually. And ideally, you want to introduce some degrees of freedom into this monolithic system so you can kind of derive some specialized discretizations regarding this coupling. This is very similar to variational flux recovery, if you're familiar with that, but in a different context, a coupling context. So the steps that really give behind the main idea of this talk are as follows. Construct this monolithic system. What is this? It's just your equations in each domain. the coupling condition on the interface gamma, which is the interface that's shared by your two components. That's just two simplicity, and your initial conditions. And let's just say we're on the first time step, so we haven't done any solving yet, and all we have is initial. We want to pose this interface condition, for instance, the bulk condition, Dirichlet-Neumann conditions, as an auxiliary equation. And this allows for special treatment of these equations. And we also want to treat the flux at the boundary as a variable, its own variable. So now we've lifted the system to become a bigger system, introducing some degrees of freedom. So at each coupling step, you somehow need to isolate the degrees of freedom of the model and of this coupling equation, the interface. You can do this once again with the Schur complement, but it's very expensive, and maybe there's better options out there for future research. But for now, this gets the ball rolling. Then you can do a second Schur complement to isolate this flux in the interface in this interface system, solve for it using the initial condition data. So you haven't even solved the models at all yet. You just kind of use the operators within them, which can be prohibitively expensive. But then finally, your flux acts as a boundary condition, and then you can do your partition solve. So you can get your cake and eat it too. You kind of have to deal with the Schur complement for the time being. And this approach, which I'm going to apply to the bulk condition, really extends the approach that my collaborators worked on in the previous paper. And my collaborators and I extended this to the bulk condition, where the standard condition is just the Neumann-Dirichlet condition that Hong talked about earlier. So now to give you a concrete idea of what I'm talking about, a more concrete idea, I'm going to present an abstract atmosphere-ocean model. And this is the notation from the Lemaitre paper that I spoke of before. And gamma is once again this atmosphere-ocean interface. So we have some abstract linear operator L, flux function F, some Dirichlet boundary operator B. So at the top, we have the model for our atmosphere. We have the Dirichlet boundary conditions on the non-interface boundaries. Then we have the bulk condition that Hong showed earlier on this interface boundary. And this is simply saying that the flux is proportional to the discontinuity in the solution. And it's derived from a drag law, actually. And you see something similar in the ocean, just with O's. And in fact, these fluxes should be equal, so there's continuity. They're equal to this discontinuity. As Hong showed, one instance of this, I use different notation, is in the heat exchange in the ocean, where you have these diffusivities, the gradient of the solution. Negative sign appears because I want to use the same normal in the equation. So NO becomes negative NA, and it's proportional to this discontinuity. And note that the strategy I'm going to present is clear if alpha is spatially and time dependent, but if it's solution dependent, giving a nonlinear bulk condition, which is the case for the velocity equations, things are more complicated. So today I'm going to restrict to the case where that doesn't happen. So let's go to the weak formulation. We're going to assume a finite element discretization in space, just for analysis purposes, but you don't necessarily have to do this. Generalize the method. That's beyond the scope of the talk today. So the first thing you want to do is you want to treat this flux interface with an auxiliary variable. I'm going to call F gamma. And this ensures conservation because now I've constrained the flux to be the same of the domain. So now I test my equations. I treat this bulk condition as an auxiliary equation, and I'm treating it, or I'm testing it with some basis function and some potentially third space. This allows you to choose a different spatial discretization, possibly both model equations. So this is an additional degree of freedom you've added to the framework. And then you integrate by parts. You know that the bulk condition is a Robin condition. And you could substitute the Robin condition into the weak form as a natural boundary condition. But you don't want to do that in the IFR framework. In fact, like I said, you want to treat this equation as an auxiliary equation with this third auxiliary variable. Now we have a 3x3 system where our three variables are UA, UO. Now we expand with trial functions. We arrive at the following semi-discrete matrix system. So as I've said, we could have chose some special spatial discretization. Third auxiliary equation, we'll just assume it is whatever it is. We'll talk about it later. What's really important in this framework is not only can you treat this last equation with a special spatial discretization, but also a special time discretization. fact, you could choose any time discretization you want that fits your purposes, that gives you the properties you want. But for simplicity, we're just going to say we apply the bulk condition, and thus f gamma time tn, the current time step. This would be consistent with backward Euler, meaning if I took this Robin condition, substituted it to the model equations, and used backward Euler, that's what I would get if I used backward Euler for the two model equations. But I don't want to do that. I want to show the flexibility of this framework. And in particular, I want to show that you can kind of cook up some odd or less odd semi-implicit type methods with this special treatment of the coupling term. So for the first demonstration, I'm going to show explicit time stepping with what I call IFR coupling. This is simply this framework I've shown you where I take f gamma in the bulk condition and I apply it at the current time step. So it's like a backward Euler representation or approximation. So if I write this down in a more compact matrix system here on the right, I have this following system where the right-hand side is nub and change. So now I have to go to the next step. I have my monolithic system that I wrote down before, completely fully discretized. I've used explicit, both model domains, but some kind of implicit approximation to the flux. And now I say, okay, separate interface degrees of freedom from the interior, which I've done here in this very complicated matrix notation, but things associated with the interface have a gamma on them, and if they have a gamma and omega, that means they're a coupling term. So you do one Schur complement to isolate interface degrees of freedom, which I've done here, and now you have these potentially complicated matrices, A and the ones existing in G. If you have a lump mass matrix, it turns out this is really simple, but in general, these are inversions that you have to actually calculate. This is currently a kink in the method because this is, of course, expensive. But if you accept this, just to get the ball rolling for principle, you can perform an additional Schur complement and solve for the interface flux on this interface system by isolating the flux at the current time step. And if you're familiar with Fedde methods, this is very similar. We've done a double Schur complement to isolate something we want. So it turns out you can do this with implicit time stepping, but that's kind of boring because that's backward Euler. So I decided I'll write down implicit-explicit coupling. It's very similar, except for we have this term being applied implicitly. We have these W matrices that appear in the ocean where we've done this implicit treatment. And now the Schur complement is a little bit more complicated because now we have to invert these mass matrices minus dT times the stiffness matrices. And so you can see that if you have an alternative to the Schur complement, which is out of the scope of this talk, but an active piece of research, you immediately gain some efficiencies. But in some cases, such as vertical heat transfer in the ocean atmosphere system, it's the case that the vertical columns are decoupled, so the Schur complement actually ends up being comparable to a system solve. But this method works out particularly well for the ocean atmosphere system. And so, just to show a toy problem, just to show that I get the correct convergence rates in space and time I'll talk about here shortly, I want to apply this method to the advection diffusion. To make it somewhat similar to the ocean atmosphere system, I want to have advection in the x direction or horizontal direction, because of course the water doesn't just fly up in the atmosphere, take off, they kind of stay separated. But then I have diffusion, namely heat diffusion in the y direction. So here I have my advection diffusion equation, I have some condition, some Dirichlet condition, the bulk condition on the shared interface gamma between these two components. So here is a diagram of the ocean atmosphere system with this gamma interface in between it. We assume this interface is, of course, stationary, it doesn't move at all. Our domain size is kind of anisotropic to represent this interface. X max is 10 kilometers and y max is 500, and the y dimension is actually 1,000 because y is centered at 0. So the y direction is 10 times smaller. We're going to use the method of manufactured solutions to give us a mildly real test case. And these results are from when I first started working on this, where I've just implemented the first thing you could think of, which is, of course, explicit coupling. And these are the results I'll show. I do have results for more exotic couplings, but let's say there's some caveats to those results, which the explanation is beyond the scope of this talk, but I will shine on it here later. So, using the method of manufacturing solutions, sinusoidal both domains, where I have a sinusoidal in the x direction for the advection part. Then I have this parabolic shape in the y direction in the atmosphere with a linear shape, the ocean. So, of course, these are some oscillations about some temperature. Do this to kind of keep the temperatures realistic so we don't have something crazy like thousands of degrees Kelvin. And then by going through the process and constraining all your degrees of freedom, realizing your solution actually satisfies the bulk condition, which turns out it was non-trivial to come up for the manufactured solution for the bulk condition. But find that once you bound all of your degrees of freedom and you add all these parameters, you get these following pictures here, like some very simple sinusoidal waves that go across the domain at some constant velocity. So I haven't specified the diffusivities of the bulk condition yet at all. I'm actually going to vary those to see if the convergence behavior changes. The time horizon is very short. I'm using implicit time stepping. Probably not the best idea, but it works for people. I have a super small time step, G stabilization, consistent mass matrices, pretty vanilla finite elements, and of course Ford Euler. And I look at the convergence rates of the L2 and H1 error in space for varying diffusivities. And so for advection dominated, you get second order in the L2, you get first order in H1. And this continues throughout all the diffusivities I choose, with the most physically realistic ones probably being these here, this medium diffusion. And of course for the large diffusion you see similar rates. And then I say, okay, these are all for matching grids, where the grid resolution is on the same both sides in space. Now, what happens if I use non-matching grids? So I still get good convergence rates. Kind of broken this problem apart and treated this boundary condition as an auxiliary equation. And now, before it was trivial to choose the space for the auxiliary equation because the models use the same finite element space. But the grid's different, they use different finite element spaces. And if you know something about Morter methods, it's typically the case that you have to choose one side's discretization or the other. And so for this test case, the ocean grid is 1.5 times finer than the atmosphere grid. It's not a huge of increased resolution, but it's not a superset, so it's legitimately non-matching at all points. I use a smaller diffusivity, and then choosing the coarser degrees of freedom to discretize F gamma, I see I still get the optimal convergence rates in space. And I see a similar convergence rates regardless if I use the ocean side. So I've kind of proved to myself that in space, everything works. But I've been a little facetious because I haven't shown you convergence rates time. That's because I've been avoiding the issue of what is known as heterogeneous time integration, where you use, let's say, an implicit method on one side and explicit on the other. And if you recall, I said this IFR method, the way I presented it, by applying it in a backward Euler way, backward Euler discretization, it was going to be consistent with backward Euler. What this means is, if you were to use an explicit method on one side and an implicit method, let's say backward Euler, on the other side, the side with backward Euler would potentially receive an optimal truncation error, or the optimal order of error. Whereas the other side that uses the explicit method with the implicit representation of coupling may receive a reduction order in its accuracy. So the question is, can you fix that framework? The answer is yes. Generally, you can. Because you've allowed yourself enough freedom to discretize the bulk condition, you can potentially do the analysis to figure out how to make this work. But the framework in which you do this is beyond the scope of this talk, unfortunately. Limited by time. Furthermore, even though you've gotten the correct accuracy by coming up with these new discretizations in this framework by adding all this freedom to the monolithic system, there's no guarantee that this is stable. You know, I introduced some implicitness purposely by applying the bulk condition at the current time step. Really, if you're going to use very complicated time stepping methods and couplings within this framework, you really need to realize some kind of stability analysis Long did to prove this is stable, even though it's accurate. And then for future work, I'd like to extend this, of course, to the primitive equations, or the velocity equations, to generalize it to finite difference and finite volume models, and not just finite element, which would be too hard. But the one looming thing is that nonlinear alpha, that bolt condition with an alpha that also depends on U. Then this method doesn't work so straightforward. It requires some type of linearization or some nonlinear. Another work in progress is extending this to multi-rate methods where you use different size time steps or even non-matching time grids in each domain, while still trying to achieve conservation. I think this is realizable in this framework as well, this variational framework. You just have to think in a more space-time way. And then finally, this is the most daunting task, but I think it can be achieved, is an efficient approximation or solution or alternative to the Schur complement. Because outright, the Schur complement is putting any structure more expensive than 2 model solves. It's actually prohibitively expensive. But in some cases, like I said, for the vertical heat exchange, special structure allows for the Schur complement to be very cheap. In other cases, this framework might allow you to find a cheap approximation to the Schur complement that still gives you the properties that you want, namely stability and conservation, but maybe an approximation that's much cheaper to find than the Schur complement. So I want to say that in conclusion, this method seems to give optimal error rates in space. I think it can be extended to be a heterogeneous asynchronous time integrator framework with a lot of work. And then lastly, I'd like to thank my supporters I'd like to acknowledge my funders, the Department of Energy Office of Science, through the E3SM project, the Kanga project. That's my talk.
Thanks, Chad. Are there any questions? Chad, I have a question.
Sure.
When you talked about using non-matching grids, I know you mentioned mortar finite elements to do the transfer, right? Essentially, you have a Lagrange multiplier that you also resolve as part of your solver. Is that
so you can realize that flux at the interface, that auxiliary variable, it takes the place of that Lagrange multiplier. So this transfer, this mortar transfer, happens in the third equation. So let me share my screen again, and then go. Okay. You see my screen?
Yep.
Okay. So in the case of Dirichlet-Neumann, it actually becomes a Lagrange multiplier system because you don't have an F gamma here when you just want the solution to be continuous at the interface.
Sure.
And so in this case, F gamma acts like this Lagrange multiplier. And then you're forced to choose a space, which is the mortar space for this equation, which then chooses the space for F gamma, of course.
Okay, I see. Because I was asking that question to see if you can replace that with a remap operator, essentially, at that interface.
So if I were to do finite volume or finite difference, that is precisely what I would do.
Okay.
Is this G operator becomes your remapping operator. Then the transpose is just the opposite mapping.
Sure.
And so I've had my mind on these through trick remapping operators for this purpose.
Okay. Yeah, that makes sense. Because I was just trying to see if it can be extended and kind of integrated with the remapping work that we're doing. And
you can have it if you have it in a functional form, it'll work, because I think these can still be functional work. You just have to think about a linear system a little differently at that point, though.